are looking at this section discussing frequency distribution for organizing and summarizing data. So the key concept is when working with large data sets, a frequency distribution or frequency table is often helpful in organizing and summarizing data. A frequency distribution helps us to understand the nature of the distribution of the data set. First, we start with what's called a raw data. In short, whatever we collect, just the way it's given, it's a raw data. Now, frequency distribution or frequency table, that's what we want to see what it is as far as definition.
A frequency distribution is the organization of raw data in table form using classes and frequencies. It shows how data are partitioned among several categories or classes by listing the categories along with the number, frequency, of the data values in each of them.
Thank you. And nominal or ordinal level of data that can be placed in categories is organized in categorical frequency distribution. The same type in essence. Let's look at a very simple example. We want to construct a frequency distribution for this case. When the raw data is collected, we just make a note of the data. This is referring to some sort of a plot type. For example, when we see A, B, B, that means the first person, the plot type for the first person is A, then the next person is B, then the next person is B again, and it moves on. So as you can see, it's a raw data, and it may not be that useful. So let's see what happens next. So we want to put it into some sort of a table. In any order that you want to set up your class is fine. This is one order, A, B, O, and then AB. I hope everybody understands what we mean by tallying. Tallying simply means for A, you can, as soon as, just for the sake of argument, you see the first one, you can tally for A and cross it out, and the next A, and so on and so forth. The idea of the tallying is to help us write the next column. So the tallying itself is really not that big of a deal. You want to be extremely careful, however. So again, let me just go back to that A, and then we have another A, we have another A here, we have another A here. So that would be the tallying in a sense. You can cross it and write it. And so now you put the numbers. So in front of A, when you count, discount as 1, 2, 3, 4, 5. You do the same thing for the rest of them, and you write the next column. So I hope you realize this is it and you're done. Believe it or not, this is the frequency distribution table. The tallying really doesn't count, okay? It's just there to help us come up with the answer. So the column that matters is the first column I'm going to refer to, and the second is not important, and the third column. The first column and the third column together give us a frequency distribution table, and you're done. End of the story. However, for more information, we can move on and do other things, such as percent frequency. Percent frequency, by definition, is the frequency divided by n. So what is n? N is the total sum in this column. That is the total size. If you add them up, that becomes 25. I hope everybody can see that. We can add them up. And then from here, for example, this one would be 5 divided by 25. This one would be 7 divided by 25. 9 divided by 25. And the last one is 4 divided by 25. And what you're looking at, this is known as relative frequency. Of course, 5 over 25, as an example, simplifies to 1 over 5. Everybody knows that, and you should do that. And then any relative frequency can be changed to a percent frequency. In essence, both of them are the same, but there's a slight difference between the two. They end up being the same number. I want you to know that. So the relative frequency is F over N, if you will, the formula that you see here. You can change it to a percentage and call it percent frequency. The other thing that I want everybody to understand is this very last formula. When you add up this column, the relative frequencies or percent frequencies must all add up to 1 or 100%. And if they don't, it is because of the rounding error or we've rounded it. So this is the synopsis of frequency distribution table. We are going to move on to the next example. The next thing is if we are given data and we want to come up with a frequency distribution table, if it's categorical, we looked at it, but if it's numerical. So first, we have to decide what is our lower class limits, and all of them will be explained with a very simple example. The smallest numbers that can belong to each of the different classes, and upper class limit would be the same row, if you will, but the largest one, the largest numbers that can belong to each of the different classes. Class boundaries, the numbers used to separate the classes, but without the gaps created by the class limits. That's important, without the gaps. Again, all of them may be difficult to follow without an example. We will shortly look at one and we make some sense out of it. Class midpoints, the values in the middle of the class, and it's very simple. Just add up the lower limit and upper limit and divide it by 2. Lower limit and upper limit divided by 2. Class width, the difference between two consecutive lower class limits in a frequency distributions. What is the procedure for constructing a frequency distribution? If we are supposed to make one up, what do we do? First, we select the number of classes. If we select too many, it really defeats the purpose. Normally, it's between 5 and 20 as far as the course is concerned and the exam questions and so forth. Normally, it's given to you. The class width, you want to approximate that. Max minus mean divided by the number of classes, that would be the width. And you have to round up always because you want to cover all the data. You want to choose a value for the first lower class limit by using either the minimum value or a convenient value below the minimum. You'll see what we mean by that. Using the first lower class limit and class width, list the other lower class limit, list the lower class limits in a vertical column, and then determine and enter the upper class limit. Take each individual data value and put a tally mark in an appropriate class so you can figure out it belongs to which class. So what do we mean by that? Let's look at this simple example, see if we can make some sense out of it. So we want to construct a frequency distribution table, FDT, and the record high temperature for each of the 50 states using 7 classes. So we are told how many classes. So I have marked the smallest number and the largest. I have put them in a different color, okay, class. So we see the smallest number, we see the largest number, and now what we do, we calculate the width roughly. Basically, we decided what we do is very simple. The largest minus the smallest. That is actually the range, it's called. So we calculate the range and we divide this by 7. So those two steps shouldn't be a big deal. So first and foremost, we find the smallest, we find the largest. Then the difference is called the range. And the range, sometimes we just write R equals max minus mean or high minus low. Okay, the largest value minus the smallest. So the width is 4.86. And so you want to come up with the width, which is going to cover everything. So 4.86 makes it crazy. We're going to go for a simple number and we're going to round it up. Always round up. So obviously, I hope everybody's clear as to why we choose 5. Now, we want to choose a convenient piece that is as the lowest number. Now, these numbers are very straightforward. So you can even choose 100 as the starting point. That is a good point to begin with. Now, so I hope everybody is clear. Now, you don't even have to use 100. You can use other numbers, okay? But if you use any other number, it has to be less than that. But you don't want it to be too small because at the same time, if you look at the width is a little bit larger than what the actual width was, okay? We chose 5, right? So for the sake of argument, if you start with something like number 90, you may not make it to the last number, to the largest number. So you got to be careful when it comes to that. And if you pick something like that, at the end, you can readjust. So 5 is easily understood. So we are going to the tables. So we know we're going to start with 100. So how do we fill up this table? All right. It's important to remember the meaning of the width. The width is 5. So the next number, okay, so the first one is the row 102. We figure out what number. It is the next one that we're going to put here 100 plus 5. That would be the lower limit of the next class. Let me make sure everybody understands how we arrive at those. So, first and foremost, I want you to understand if the first one is 100, the second one is 105. Now we're going to add 5 this way. Add the width equals 5. So 100, 105, 110, all the way to 130. Why is that? Count 1, 2, 3, 4, 5, 6, 7 classes. Now, I want to look at the upper boundary. The upper boundary, the way it is class, if you use one class, okay, for example, look at the very first one. If you look at this class, the width using the same class is defined as upper limit minus lower limit plus 1 unit. I want you to pay attention to this formula I'm giving you. I'll put that in your formula sheet as well. The width is the upper limit minus the lower limit plus 1. So you have the width, you don't have the upper limit yet. You have the lower limit to be 101. Let me explain the 1 unit. If 1 represents 1, so be it, but 1 unit may represent 10,000, or 1 unit may represent 0.1. That's why I say 1 unit instead of simply 1. And this is simple math, everybody can handle it, and it becomes 104. And then after you find the very first upper limit, keep on adding 5. Okay, class? 104 plus 5, 109, plus 5, plus 5, and we get to the end. Now, when we get to the end, make sure you see we have 134, and the last one is also covered. Okay, so this last one is also covered. We are okay with that. Otherwise, we have to rethink what we are doing. So this is it. This is class limits, and we are okay with that. Now, we are going to look at the class boundaries. Now, without the class boundaries, by the way, class, we fill up the third column, which is the frequency, we are done. The frequency distribution table is done when you have this very first column and this last column, which is frequency. Now, how do you do that? It's by tallying. However, let's look at the concept of a class boundaries. The way the class boundaries work is very simple. Remember, there is a gap between 104 and 105. Everybody can see that, right? Now, boundaries say there is no gap. So you add up 104 and 105, you divide by 2. So 104 plus 105 divided by 2. And that's 104.5. And that is the upper boundary of the first and lower boundary of the second class. So take a look at those two numbers only, everybody. 104.5. I hope everybody understands how we arrive at 104.5. What about the rest? Very simple. Add the width. All of them. Just add the width. For the first boundary, the lower boundary of the first class, subtract 5. So notice these two are the same. These two are the same. So that's the idea of the boundaries. So how do you come up with the boundaries? You come up with the upper boundary and lower boundary of the upper boundary of the first class, lower boundary of the second class simultaneously, and the rest you just add the width. For the lower boundary of the first class, you subtract the width. Now, what about the frequency? Very simple. You just go and figure out where everything belongs. Now, I didn't put the tallying here, everybody. I want you to know there is no tallying here. But just for the sake of argument, between 100 and 104, just as an example, okay, I want you to know that 100 is in that class. This is one of it, okay? Is there anything else that belongs to that one? Because that's fairly short. I want to make sure everybody gets that. Is there any other number that you can see that it's between 100 and 104? It does include 100 and it does include 104.
104.
So we have a 104 too, right?
Yes.
So therefore, the frequency for the first one is 2. You can figure out the rest as well. Now, what I want to add is this, the difference between the limits and the boundaries so everybody understands how it works. The way the class limits work, if you look at the very first one, 100 to 104, 100 is there, so is 104. If you look at the boundaries, 104.5, I'm just discussing the very first one. 104.5 doesn't belong to the first class. If you follow the boundaries mean everything starting from 9.5 all the way to 104.5, not including 104.5. 104.5, if it happened to be there, belongs to the next class. So I hope it's clear so we can move on.
Professor, I just had one question. So,
Of course.
You've put 104 plus 105 divided by 2?
Absolutely. In order to find the boundary of the boundary for the first class, the upper boundary, and the lower boundary of the second class. Here's another one. Take a look. If I were to find the boundaries, look at these two. If you add these two up and divide by 2, you get 119.5. So take a look at the upper boundary of this class, which is 1, 2, 3, 4. The upper boundary of class, fourth class, I hope you see this is class 1, 2, 3, 4, 5, 6, and 7. So for the fourth class, the upper boundary is 119.5, and the lower boundary for the fifth class is the same. Does that answer your question?
How did you get first a lower class boundary?
Lower class boundary, that was a choice. Take a look at this one. You have to choose a convenient piece that is either smaller than the minimum value you have, or it's equal to that. So we chose 100.
What is I'm sorry, I might have said something wrong. What I meant is, how do we choose 99.5 for the class boundaries?
No, we don't choose it. We calculate it.
Okay.
Okay. 100. Okay. So 104.5. Okay. Look at, so everybody's okay with 104.5 as the upper boundary of the first class? Yes? Everybody?
Yes.
Subtract 5. What do you get?
99.5.
Why are we subtracting 5?
Because that's the class width.
That's the class width. Beautiful.
Okay, perfect.
Okay.
Thank you.
I actually have a quick question. So if we do have the value 104.5, it would go in the second class, not in the first class?
It is the upper boundary of the first class, and it is also the lower boundary of the second class.
So when we were calculating like the frequency and we had the value 104.5.
Yeah, if you had, exactly. If let's assume the number 104.5 is also part of the data, then it belongs to the next class. That is by definition of a boundaries.
Okay, so then we
for
would count
example,
it in the 8, not in the 2?
Exactly. Yeah, exactly. Here's another one. How about if we have a class, if we have number 124.5 as a piece of data, where would you put it? Number 124.5. Which class?
Six.
Sixth class. Is everybody clear? How about 129.5?
7.
That's it.
Okay.
Is everybody okay with that?
Yeah.
All right, let's move on. We want to come up with frequency distribution table. So just to make sure, okay, there's a lot of piece of data here. To do that, this is drive-through service for fast food. So we got to figure out the width. All right. So I hope everybody is clear as to how we arrive at this. The width ends up being a whole number 45. Now, if you want to start with 83 as the minimum value, there's nothing wrong with that, but it's really not a convenient spot to start. And notice the width, which is 45. Again, we want to make it nice and easy. If you decide to go with any other numbers, just to make things up, let's say instead of the width being 50, you want to make it 46. There's nothing wrong with that, but it's not a nice and easy number. I hope you understand the concept. So when you go from 45 to 50, it is your choice. We are choosing to make life easy, okay? And so this is another one. So how do we calculate the width? The range divided by the number of classes. And we already know that we have 5 classes. Take a look. We have 5 classes, okay? And so with that being the case, we can start with number. We can start with 80, okay? We can start with 75. But you really don't want to go lower than that. Maybe even 70 might work because it's important when you're done. The largest number, 308, must be included. If it's not, then there is something wrong. So it's important to know that a lot of things is really up to you. Okay, so the class width is 45 and you change it to 50. Okay, when you calculate it, where do you begin? You begin wherever you like. You can begin somewhere smaller than 83. You can start with number 80. There is absolutely nothing wrong with that. I hope everybody is clear. So with that being the case, let's say we start with 75. Now, can you tell me how we arrived at the rest of them? How did we come up with 125, 175, 225, and 275?
You keep adding 50.
Beautiful. Now, how do we get, I'm just interested in the first class, 75 to what? To what number? So my first class is 75 to
124.
one more time, 124. Because remember, the width is upper limit minus lower limit plus 1. And remember, by 1, we mean 1 unit. So it's not 125, it becomes 124. Then all you have to do, add 50 to that column. Keep on adding 50. So I hope you see that it's not difficult to find these numbers. Never mind the frequency, I want to discuss the upper limits. So what are the lower limits? The lower limits are 75, 125, 175, 225, and 275.
I just have one quick question, Professor.
Yes.
We made the width 50 just out of convenience in order to better
Exactly.
organize that time,
It is absolutely up to you, and it must be larger than 45. So in other words, you can't say 40. That would be a wrong choice.
Okay.
You can choose 60, but it's way off. You know what I mean?
Yeah.
It's out of convenience, absolutely. So 50 is very straightforward. The thing is, why did we choose 75? I want to stick with that, but you can choose 80. In fact, I highly recommend, if you have time, try it with number 80 and see how that works. So the lower limits and the upper limits are clear. How do we come up with this one? As you can see, it's just a matter of tallying by now. It does take some time to do the tallying. Okay. Sounds good, everybody? Now, the next thing, so practically we're done here. I want you to know that, but we're going to add some stuff for information. Now, obviously, n adds up being 50, the same number that we had there, the total size. Okay, if you add up, that's another thing that you want to be careful. You always add them up, make sure you come up with the same size. Otherwise, we've made a mistake somewhere. So this is a good way to check your work. This is a good way to check your work. Now, as far as finding the relative frequency, as always, okay, remember the relative frequency would be what? Just the frequency divided by the total size. So the relative frequency for the first class would be 11 divided by 50. The second one would be 24 divided by 50, so on and so forth. So how do you calculate the relative frequency? It's very simple. Divide f by n, okay, class? Divide f by n, and you get to the answer. I hope it's straightforward. And how do you change it to percent frequency? Again, you should have no problem doing that basic algebraic technique, okay? You can always change to a percent. And remember, they must add up to 1 or 100%. I can't really emphasize this enough. The only time it doesn't, when you have a round of error, okay? So that's one of the things you want to be careful. Don't round it too early, okay? If you have to round it. All right, let's move on. All right. I'm assuming everybody is comfortable with what we did, so I'm going to repeat the same table, okay? So what you are looking at, class, what you are looking at is from the previous page, frequency distribution table, FDT, frequency distribution table. Now, we are interested in cumulative frequency distribution table. So we want CFDT. Okay. How do we arrive at it? There are three ways to do that. So I'm going to look at all ways, and my favorite one is this one. So how do you come up with CFDT? You look at the first column, and the lower limit of 75 remains for each and every one of them. What does it mean? It means cumulative. It means from the get-go. And therefore, 75 to 124 is the same good old 11. So that repeats. But what happens to the next one? Now, 11 plus 24. What happens to the next one? 11 plus 24 plus 10, and then you add 3, and then you add 2. Okay? Or you may use this method, as some texts they use, less than 125. They use the lower limit of the next class and they write it less than that. Or they use the boundaries and they say less than the upper boundary of the first class. But all of that mean absolutely the same. I'm more interested in that. However, and this is what I like, if we had on-campus exams, this is what we would use. I mean, either one of them, you get full credit from me. However, as you do your homework or exam questions, just follow the way they want you to do it, and you get full credit. I hope everybody understands the meaning of this table, the cumulative. Sounds good? Okay, so it's very simple. You add them up. The thing that you want to be careful is the following. This one, this number must always be n. If you haven't made a mistake, this must always equal number n, whatever it might be. All right. So that's that. Let's move on. Could somebody read this one for us, please?
Critical thinking using frequency distributions to understand data. In statistics, we are often interested in determining whether the data have a normal distribution. 1. The frequencies start low, then increase to 1 or 2 high frequencies, and then decrease to a low frequency. 2. The distribution is approximately symmetric. Frequencies preceding the maximum frequency should be roughly a mirror image of those that follow the maximum frequency.
Thank you so much. Later on, we will pay more attention to this. This is the core of the course, and it will look something like this. This is called normal distribution. Now, of course, in reality, nothing is 100% normal, but something close. That's the idea behind that. Okay, somebody read the second part for us, please.
Gaps can show that the data are from two or more different populations. However, the converse is not true because data from different populations do not necessarily result in gaps.
Thank you so much, everybody. All right, so let's look at this table, okay, just as an example. This shows the frequency distribution table, okay, FDT, for what? Weights in grams of randomly selected pennies, okay? And so the idea is, and again, we may not know the information, and I don't expect you to know this information, but the idea behind this is that we notice there is a gap. So probably we have two different groups, and we may stop at that. However, a piece of information says pennies made before 83 are 95% copper and 5% zinc. After 1983, things are different, 2.5% copper and 97.5% zinc. So that's why it changed its weight on the average. Okay, so again, that's a piece of information we may or may not have, and it's not important. The gaps can sometimes reveal things. All right, we're going to move on. Sometimes when we combine relative frequency is or frequencies, if you will, then we can get something out of it. So in this case, the table shows the relative frequency distribution for the drive-through launch service time for a fast food. So we are dealing with fast food and coffee shop, okay? And so it shows the time. For example, if we discuss the very first class, the fast food doesn't give us any piece of data, but the coffee shop, 22%. And when you move forward and you look at this, you should be able to see that there is a big difference. And normally, if you go to a coffee shop, the service takes place in a very short time. That makes sense. Whereas fast food is not as fast. That is a normal expectation class. So, all right, we want to identify the information here, such as class width, midpoints, boundaries, and so on and so forth. All right, class width. There are really two ways to do that. You can pick any two classes, any two consecutive classes. Whether you do the upper limits or lower limits makes no difference, class. The difference is the answer. Or if you pick one specific class, upper minus lower plus 1. So I hope everybody is clear as to why the width is 100. By the way, if you count from number 100 to 199, including 100, there are 100 numbers. I want you to know that, not 99. So one more time. If you count from 100 to 199, including the endpoints, namely 100 and 199, that is 100 pieces of numbers. So the next one is asking for the midpoint. The midpoints basically add up, divide by 2. So for the first class is 100 plus 149 divided by 199, I'm sorry, divided by 2. And then you don't have to calculate the next one, add the width. So all you have to do, calculate the first one, class, which is 100 plus 199 divided by 2, giving you 149.5. Then add the width. Add the width. That's all. So you calculate just one of it. That's all there is to it. And what about the boundaries? Remember how we arrive at the boundaries. Let me just use a different color again. So add these two, 199 and 200, and divide by 2. The midpoint of the two is 199.5. And then just keep on adding the width. And for the first one, subtract it. Finally, number of subjects, add the frequencies. Add them up. 25 plus 92 all the way to the end. That should be very straightforward. All right, let's quickly look at the last question before we move on to the next section. All right, could somebody read the question, please?
Analysis of last digits. Weights of respondents were recorded as part of the California Health Interview Survey. The last digits of weights from 50 randomly selected respondents are listed below. Construct a frequency distribution with 10 classes. Based on the distribution, do the weights appear to be reported or actually measured? What do you know about the accuracy of the results?
I'm going to assume everybody can make up the table very nice and easy. When you look at the last digits are 0 all the way to 9. So you can tally, you can make up this table. I'm assuming nobody has any problem setting it up. Okay, but when we look at this, and this refers to what are we measuring here? A lot of weights, right? As you can see, we have too many zeros and fives. So that means what? Basically, it was approximated. And so it can't be accurate. And by the way, after 0 and 5, number 8, we have a lot, okay? Sometimes, I don't know, instead of saying 170, we say 168. That may be the case. But more importantly, too many zeros and then too many fives, and that has the indication that we didn't actually measure.
May I ask a
All
question?
right, go ahead.
How do we calculate the probability that that these frequencies are actually true? That this isn't inaccurate data? Because there is some chance that, for whatever reason, there are, but a low chance, granted.
No, understand. Understand what's happening. This is based on the data. You remember a lot of stuff in statistics could be interpreted subjectively. We are saying if this we don't know that for sure. It could be, yes, by chance. Yes, you're right. It could be that a lot of people they measure and end up having weights that end up with 0. But if you are looking at a normal distribution, it can't happen that 0 is more than the rest of it. So based on your simple observation, you say, well, this makes no sense to me.
Okay, so it's a subjective kind of.
Yes, but more importantly, it could be subjective, but at the same time, it's a decent guess. How come we have so many zeros? If it's a normal distribution, the normally distributed, and the weight is normally distributed, then zeros and ones and twos and threes and fours, and they must be close. They can't be that we have too many zeros. Okay.
Okay.
I hope this answers the question.
Oh, yeah, absolutely.
We looked at the previous section, FDT, frequency distribution table, and what they mean. Frequency distribution table refers to organization of raw data into a table. We have the lower limit, upper limits, class boundaries, class midpoints, and class width. Each one is calculated accordingly. And the procedure was discussed as to how to come up with the frequency distribution table. All right. What we are going to do in this section, going to look at the histogram, and while a frequency distribution is a useful tool for summarizing data and investigating the distribution of data, another tool would be histogram, which is a graph that is easier to understand and follow. A graph consisting of bars of equal width drawn adjacent to one another, that is the synopsis of what's a histogram. The horizontal scale represents classes, quantitative data, and that's important to follow. And the vertical scale represents either frequencies or percent frequencies. Important use of histogram visually displays the shape of a distribution, shows the location of a center and the spread and outliers. So here's a simple example. Again, we have seen this now. We want to look at its histogram. So I hope you see the concept is very simple. You go with a simple grid, and along the x-axis, the horizontal axis, you can put these numbers. The way the horizontal axis works, you have three choices. You can choose to use the limits. You can use the boundaries. You can even use the midpoints. However, later on, we discuss a graph called ogive, and in that case, we have only one choice, and that is using the boundaries. And because of that, it's a good practice that we use the boundaries along the horizontal axis. So I would use the boundaries here. So you would put, for example, 99.5 here, and then 104.5, and you move on, you make up your scale. Now, on the vertical axis, you have a choice of using frequencies or percent frequencies or relative frequencies. Which one do you use? Whatever that you are asked to use. In this case, we use the frequencies. For example, if you look at the very first one, and the height, you can go, in this case, 2, 1, and so forth. So you can go from the scale, if this is 1, for example, go all the way to, I don't know, what is the largest one? 18. You can even scale it such that the largest one, I don't know, is 20. And you just pay attention to your scale. I hope everybody can come up with this simple histogram. The bars are adjacent. Look at the bottom as your horizontal axis. It contains the boundaries. And again, I'm going to repeat, you can use the boundaries, you can use the limits, you can even use the midpoints. But the best choice, boundaries. Why? Because there's a restriction for some graphs that they must use the boundaries. Therefore, it's a good choice to stick with that. Now, your vertical axis, notice, in this case, is frequency because frequency is given. If they want us to do percent frequency, ultimately, it really looks the same. I want you to know that it doesn't make that much of a difference. Whether we use frequency or percent frequency, the shape is very similar. However, you want to be careful with your scale. So just for the sake of argument, if you pick any of these, so if you look at this one, this has number 18, and this is the height 18. So this one has the height 8. To the right of it, this has the height 13, and so on and so forth. So I hope it's clear. So coming up with the histogram, bars are adjacent. The horizontal axis uses the boundaries. Vertical axis uses frequencies in this case. Relative frequency histogram, again, as I said, it works in the same manner. Coming up with the histogram for the given, it's really not a big deal. As far as the horizontal axis is concerned, just the way it's given, you can choose to use 75 to 124 as the first one, and so on and so forth. But you can also make up your boundaries. Remember how we make up the boundaries. Look at this one. So the upper boundary for the first class is 124.5. So I'm going to write just the first class. So 75 to 124. That gives us here 124.5, which means the next class uses the same lower boundary, 124.5. The width is 50, so you can subtract 50 and you can add 50. So remember, the width is 125 minus 75, which is 50. So if you add 50 to 124.5, you get 174.5. You can subtract 50 from 124.5 and you get 74.5. And this is the histogram that you have. very straightforward. And the largest one, of course, has the frequency of 24. So this number, this corresponds to 24, 11, 10, 3, and 2. Now, relative frequency is defined as frequency divided by total size. So the relative frequency for the first class would be 11 divided by 50. The next one would be 24 divided by 50 and so on. Remember that. I think this question was done already. And remember the RF, the relative frequency, must add up to 1 or 100%. So this must add up to 100%, or we've made a mistake. The only time that it may not be 100% is due to round off error. If you have, for example, 99.9999%, or if you have 100.000, bunch of zeros and then 1%, that is acceptable. And so you graph it accordingly, and they look very similar. If you do the relative frequency or percent frequency properly, they end up giving us the same answer class. The shape is very close. Now, the thing you want to be extremely careful of when you set up your graph, this must read frequency, this must read percent. Make sure you have them accordingly. So the point being, histograms, whether we use the frequencies to make up the histogram or relative frequencies to make it up, the shape shouldn't be that much different. When we do histograms, here's what happens. We explore the data by analyzing the histogram to see what can be learned about CVDOT. C stands for the center of the data. V stands for the variation. D is for the distribution. O stands for the outliers. And T is time. And there are some common distribution shapes. Something that is bell-shaped, also known as normal distribution. A uniform distribution, the heights are the same or almost the same. Skewed to the right or positively skewed, or skewed to the left or negatively skewed. Again, those are just the shapes. I think most everybody is comfortable with this and remembers this stuff. Again, a normal distribution, it's almost bell-shaped, and we call it normal distribution. As far as skewness, a distribution that is skewed, if it's not normally symmetric, extend to one side. If it extends to one side, such as the right side is skewed to the right, or maybe skewed to the left. We are in essence repeating what we just mentioned. So if we have the histogram drawn properly, it sort of gives us the information that were mentioned here. Now what happens if the histogram is given? In this case, the histogram, when we look at the bottom, it says weights of the porters in grams, and the top, the vertical axis is the frequency in which it occurs. So use the histogram, and we want to find the following. We want to come up with the number of subjects. The reason it says estimate the number of subjects, because sometimes it may not be easy to read from the histogram. It may be that it's close, and that's accepted. The width, boundaries, and there's a gap or what's happening with that is a normally distributed. Now, to estimate the number of subjects, it simply means add up the frequencies. So each bar has a height. You estimate the height, you add them up. So I hope everybody's clear the concept. Again, I'm going to put number 12 here for the first one. And if somebody reads it, I think everybody should read 12. But if you read, okay, maybe you think it's 11, it's not that big of a deal. I want you to know the concept is whatever that number is, look at the next one and the next one and the next one, add them up. That's how we estimate the number of subjects. What about the width? First and foremost, let's talk about the third one, the boundaries. These are the boundaries for the first class. And then these two would be the boundaries for the next class. And then you move on all the way to the end. I hope everybody is clear. So we have number one, we have number three in essence. What are the boundaries for the first one is 5.5 and 5.6. And therefore, the width is the difference between the two. When you want to calculate the width, if the boundaries are given, So the width would be upper boundaries minus the lower boundaries of the same class. Whereas in the limits, it was upper limits minus lower limits plus 1 unit. Okay, don't mix them up. Okay, so we have those. And there is a gap here. As you can see here, the height is 0 in this case. So again, can be explained. And whether it's normal or not, clearly it's not a normal distribution. Number of subjects, you need to add those heights, 12 and 20 and 8 and all the way to, then there are 80 subjects, in this case, quarters. The width, as I mentioned, 5.6 minus 5.5. And the boundaries are given for the first one. There is a gap, and that means there are two different groups, and then it's again from two different eras. The first set is 40, the second set is also 40, but two different eras. You can look them up, and clearly it's not normally distributed. Now, I want to explain one more topic that I want to go through that fairly fast. We don't dwell on it too much, and that's assessing normality. This is a piece of information, pre-1964 versus post-1964. The way it was used, 90% silver plus 10% copper, and then afterwards was copper and nickel alloy. So that's why different weights in any event. If we want to look at normality, normal quantile plot, here's what we do. Could somebody read this one for us, please?
Normal distribution, the pattern of the points in the normal quantile plot is reasonably close to a straight line, and the points do not show some systematic pattern that is not a straight line pattern.
Okay, so the idea is that there seems to be a straight line if we set them up. Could somebody read this one for us?
Normal, if the normal quantile plot has either or both of these two conditions, the points do not lie reasonably close to a straight line pattern. The points show some systematic pattern that is not a straight line pattern.
Thank you so much. So this is not a normal distribution. Now, what I want to discuss is this last piece, okay, which really puts all of it together. Could somebody read this one in blue, please?
Normal quantile plot. A normal quantile plot or normal probability plot is a graph of points x, y, where each x value is from the original set of sample data, and each y value is a corresponding z-score that is expected from the standard normal distribution.
Thank you so much. So what is normal quantile plot? It has two, the pairs are as follows, x and y. Y is equal to the z, which is x minus mu over sigma. We will discuss that with more details as we look at the z scores, and that is the normalization score, standard normal distribution, and it's coming up. But that's the idea, you plot those